Welcome back to the workshop. We want to continue taking a look at the third section of the appendix, methods of proof. And we want to take a look at another example of a direct proof. So we have an implication that we want to prove, and when we prove an implication, we do that by assuming that the premise is true and showing that the conclusion is true. By showing that the premise and conclusion are true, we see that the implication is true. Again, if we think back to the truth tables, we only had 4 situations. Both were true, in which case the implication is true. When the premise is true, but the conclusion is false, we actually have that the implication is false. So we're not expecting to have that scenario. What we want to find is that the implication is true. So the last two possibilities were when the premise itself were false, and in that case, the implication is true. So the only scenario that we have to worry about is when the premise is true. So we start by saying, hey, I want to prove this implication. So proof, we set up the problem, let the numbers be integers or real numbers, whatever we need there. And then we assume that the premise or that the hypothesis is true. And then we use the information that we have, whatever the setup was to the problem, whatever assumptions that we made for the premise, and then we use those along with definitions, known ideas, theorems that have already been proven true. We use those to show that the conclusion is true in our implication. So once we have that the premise and conclusion are true, then we know that the overall implication is true. So we already saw one example of this. Let's take a look at another. All right, so here we have that suppose A, B, and C are integers. What we want to prove is that if A divides B and B divides C, then A, in fact, also divides C. So essentially what we're doing is we're taking a look at the transitivity property for the relation divides. So that's some language that we took a look at quite a while ago back in the chapter regarding functions. So here, again, if A divides B and B divides C, then A divides C. So if you're not sure what it means to divide, we have a formal definition along with a notation, but we also have just kind of a general idea. So if I go use the bottom of the previous page and maybe write this in red because it's just a kind of a side note, we might notice that 3 divides 15, right? Because you might think to yourself, I can take 15, divide it by 3, and I get 5. Since 15 divided by 3 is an integer, we would say that 3 divides 15. And this is the right idea. However, it's more commonly written as, or the definition is rather, 15 is equal to 3 times 5. So we know that 3 divides 15, since 15 can be written as a multiple of 3. That is the definition of divides. So we'll utilize that here. So what we would like to say is that M divides N, excuse me, if and only if N can be written as M times K for some integer K. So M divides N if and only if N can be written as a multiple of N. Now there is a notation for this, so M divides N is written that M divides N. So you might see this notation used. We won't use it here just because the text that we're working with doesn't, but you might be looking for additional resources. And if you encounter this notation, that's what that notation would mean. So here we're assuming that A divides B and B divides C. And we want to show that A divides C. If you wanted to consider an example of this, we could see something like, let's continue to work with these numbers, right? 3 divides 15. I said I wouldn't use that. Let's not. 3 divides 15, and 15 divides 30, right? 15 divided by 3 is 5. 30 divided by 15 is 2. So we have 3 divides 15 and 15 divides 30. Or we can think of it as 15 is 3 times 5. 30 is 15 times 2. That's fine. And we can see pretty clearly that 3 divides 30, right? Because 30 is 3 times 10. So we can see an example of this, but this is, right, 3 divides 10. This is just an example. This is not a proof. We have observed one scenario in which the theorem is true. We haven't shown that it is always true. Okay, this is just one example of when it is true, not a proof of it. So in the proof of it, we have to keep our numbers in terms of A and B and C. Of course, some additional numbers will be introduced because we'll have K, but it's still K. It's not a specific number. So we want to write our proof. We begin by indicating that we're writing a proof. Proof. Then we make our assumptions. So let A, B, and C be integers. So, right, we need that A, B, and C are integers. And we want to assume the premise. And the premise is, so assume that A divides B and B divides C. So that is the premise. We're assuming that the premise is true. Why? Because when the premise is false, the implication is true. So we don't have to worry about those. When we want to show that the implication is true, we start by assuming the premise is true, assume that A divides B and B divides C. And then we show that the conclusion is true. We want to show that A divides C. How can we do that? Well, we just need to use the definitions that we've now learned. How we can write this relationship knowing that we have one number divides another. So then we can write, actually, let's write it this way. Since A divides B, we have, since A divides B, we can write B as a multiple of A. So B is equal to A times K for some integer K. All right, similarly, since B divides C, we have, now here, is it necessarily true that it would be C is equal to BK? Well, I'm already using K here, so once I have that specific number, it's generic because I don't know what that number is, but it represents one specific number. We don't know. So C is a multiple of B. I don't want to use the same letter. I want to use a different one. So I'm going to use L. C is a multiple of B for some integer L. Excellent. So I have a way that I can represent B. I have a way that I can represent C. And what good does that do us? Well, I want to show that A can divide C. So I want to write that C is equal to some multiple of A. So I want C to be equal to some multiple of A. Well, I don't have A here, but B can be written in terms of A, so I just make that substitution. So substituting, let's see here, substituting B with A times K in the last equation gives, or we find, let's say that, and I'm replacing B with AK because B is AK. C is equal to AK times L. So in order to emphasize that C is a multiple of A, we can recognize that that multiplication is associative. So it doesn't matter what order I multiply it in. So I can say A times KL. So I grouped A and K, but I get the same thing when I group K and L. Since KL is an integer, right, what I've done is I've written C as a multiple of A. So A divides C. But I don't have that until I know that this number, right, until I know that KL is an integer. So I need to specify that. I know it is, right? K is an integer, L is an integer. So KL is an integer. I don't need to go through all of that language, but I should and I need to recognize that KL is an integer. So since K times L is an integer, we actually have that A divides C. Right? Because when we can write C as a multiple of A, when we can write N as a multiple of M, we know that M divides N, or in this case, that A divides C. All right. So we have, what have we done so far? Well, what we've done is we started with our little, you could call them a part of your assumptions, and that would be fine. But we need to let the numbers be integers. And here, what we've done is we have assumed the premise or the hypothesis rather. And then here, I made some manipulations. And definitions. That's what I would consider each of these. Those are both definitions, right? What does it mean for a number to divide another number? Well, it means that we can write it in this way. So again, here we're using a definition as well. But this gives us, we found that the conclusion is true. A divides C. Excellent. So now, so Q is true. So now that we have that Q is true, we can restate the implication as a truth. So we want to say, thus, if A divides B and B divides C, then A divides C. Of course, we want to indicate the end of our proof, so we draw our square and color it in. And that's it, right? That's the structure of a proof. We indicate the beginning, we indicate the end, we have an assumption, we assume the premise, we perform some manipulations, cite some definitions, use well-known facts to show that Q is true, so that way we can conclude that P implies Q is true. Thus, if A divides B and B divides C, then A divides C. That's exactly what we showed here. All right. In our next video, what we'll do is we'll take a look at direct proofs again, but we're going to look at a direct proof that requires multiple cases within that proof. Okay. So I'll see you guys back in the workshop very shortly.